So yeah, it's my pleasure to welcome Christine Chen. She's going to be talking about data-driven dispatch for models in power systems. So Christine is an assistant professor in electrical and computer engineering from the University of British Columbia, so not too far from Seattle. And she's in their energy systems group, or electric power and energy systems. Her research is focused on power system analysis, monitoring, and control. She got her bachelor's degree from the University of Toronto, 2009. And then she did her graduate work at the University of Illinois at Urbana-Champaign and finished her PhD in 2014. She has a Best Paper Award from the IEEE Transactions on Energy Conversion, and she serves as editor for some of the power journals. So I'll hand it off to you, Christine. Feel free to take it away.
All right, great. Thanks, Brian. Thanks for the introduction, and thank you for inviting me. It's really a pleasure to be here today. So data-driven optimal DER dispatch using estimated sensitivity models. And oh, now I can't switch slides. Oh, here we go. Okay. So the work that I'm presenting today was largely made possible by an industrial collaboration with this company called Imbala Power Networks, along with funds from MITAX and NSERC, which are our federal funding agencies. Imbala's main technology is basically a software platform that coordinates controllable assets at the grid edge, and so-called distributed energy resources, which we'll talk about today. And they were recently acquired by a company called Generac, which I had never heard of, but they're mostly known for manufacturing portable backup generators. And now they're looking to expand into kind of the grid services provisions kind of area. I also want to acknowledge the work of Severin Novak, who is the main driver behind this work, really. And so he's a student that I'm co-supervising with a colleague at UBC Okanagan, which is a different campus at UBC. I'm really sorry, but I'm having trouble like switching between like my monitors again. Like my mouse is stuck on, oh, here we go, sorry, that's good. Okay, yeah, all right, sorry about that. So before we kind of get started, maybe it's worth mentioning that UBC actually has two campuses. So here I'm showing Seattle, which you guys should know with a big W down the bottom. And I'm in Vancouver in this upper left star. So we have a campus here, which is our large campus, sort of situated on this peninsula. And we have a different campus in the Okanagan Valley. And so my colleague Li Wei is actually with the School of Engineering there. And so a silver lining of the pandemic is that really, while it used to be kind of like a chore or an inconvenience to work with our colleagues at UBCO, it's sort of been normalized in this past year, and it's sort of like nothing now, right? So in terms of kind of moving into the technical topic of today's talk, which is related to the coordination of assets in the distribution network. To set the context, I just want to kind of describe the power network a little bit, or the power system. Traditionally, the power electricity is mostly generated by large-scale units that are located farther away from load centers. And these are kind of larger, turbine-based, nuclear or fossil fuel-based generation. Then the power is transmitted through high voltage transmission lines, closer to, and then stepped down in voltage closer to the load centers. So for example, in British Columbia, most of our power is produced in hydro dams way up north in the interiors. And most of the loads are, of course, where we are, which is called the Lower Mainland area, and so there has to be a really long distance high voltage transmission. And then when the voltage is stepped down from this high voltage transmission side to the low voltage, this network that I'm showing here is essentially what's called the distribution network or the distribution system. So here, obviously, we have lots of loads because it's the load center. So there's lots of loads at all the different electrical nodes in the system. Traditionally, these loads are basically just passive, and they essentially just, use whatever power, whatever amount of power whenever they like. And so that actually kind of reflects our expectations for a high level of power availability and quality in our system. Now, in order to maintain that power availability and quality while serving the loads, we have to make sure that the voltages across this network and the currents as well don't violate operational limits. So for example, if loads draw too much current, then it may cause over currents in certain equipment that's rated for a particular maximum level of current. And some loads only operate within a certain range of voltages, or operate at least most efficiently or most effectively within a certain range. So all that is to say is that the system requires some regulation on the current and the voltage. And this can be done sort of at a local level or from a global kind of control perspective. So conceivably, in the case of the global control, then we would need to have some knowledge of the network over which this power is delivered, right? So the lines and the line parameters, the resistances, reactances, the switch statuses. So you can see in this network, there are some switches as well, like this one and here, in general, just sort of all sorts of network related parameters, load levels, transformer settings, and set points for just like any number of devices in the system, right? So it would be good to know if we wanted to control the variables that are pertinent in this network, to know the network, right? And on top of all of this, right now we're motivated to also reduce fossil fuel-based generation. And of course, this is in an effort to counter the effects of greenhouse gas emissions in terms of global warming. And a really good way to achieve kind of both of these goals, the goal of control as well as the goal of reducing fossil fuel generation, is the integration of these distributed energy resources, or DERs for short. And examples include things like solar photovoltaics, wind, battery storage, electric vehicles, and even controllable loads in demand response, for example. And so when suitably coordinated and controlled, these devices add to the flexibility that we have to control the distribution network. And an added benefit of having DERs is that you're actually generating power at close to where you're using power, so there's not as much of a need for that really expensive high voltage transmission infrastructure or the losses that would be incurred along the way. Unfortunately, on the flip side, the integration of these devices kind of largely invalidates the basis that kind of our distribution systems were designed upon. So for example, we used to assume that there would just be one-way transmission of power, right, from the distribution system into the loads from the transmission system into the loads of the distribution system. And what this means is that we generally would see a pattern of voltage drop along the feeder. Moreover, we can also kind of no longer rely on the fact that the loads would be mostly conforming to a predictable pattern, because now the loads could be, or the net loads could be affected by behind the meter solar generation, which could go up and down depending on cloud cover or solar irradiation. And since the distribution grid was not really originally designed for this type of two-way flow and sort of the coordination of an interaction among these different diverse devices, there's kind of a growing need now to coordinate and optimize DERs toward reliability goals or performance goals, or minimizing losses or costs of asset management, any number of metrics. And so with that in mind, then our goal is to basically, in this statement, determine optimal set points for DERs that are available in the system now for us to play, control, and tweak the outputs of. And we want to set these DER outputs so that they minimize some cost metric while satisfying operational constraints. Okay, and we talked about operational constraints in the sense of you could have voltage limits or current limits and things like that. So a very general solution is to formulate kind of this optimization problem here, right? And in general, this optimization problem can be a generic function of net loads, which is I'm going to use the letter Y. So these are uncontrollable, so just like imposed upon us, uncontrollable loads. It could also be a function of voltages. You may want to minimize the excursions of voltages, so collected in X. And certainly you want the voltages to lie within a certain range between some minimum and some maximum. Also, the cost function could be of the DER outputs. So this could be like the cost of installing and operating the DERs with this controllable output U. Right? So controllable U, uncontrollable Y, and then X are just sort of voltages and that represent operating point of the distribution system. And also the controllable U's are constrained within some space that's, you could think of it as the operational capabilities of the inverter that the DER is connected through, for example. Okay, and lastly, very importantly to what we're talking about today, is that all these variables are coupled through this so-called power flow equations, this set of nonlinear equations that essentially describe circuit laws that nodal voltages and net loads must adhere to over this network. Okay, so implicit in this formulation of these power flow equations are various parameters that that reflect the network topology or the line parameters, switch statuses, etc. So this is this problem, this generic form of the problem is in fact made difficult to solve because of this nonlinear power flow equation. It renders the optimization non-convex, and a lot of effort, including really important and seminal work done by the colleagues here at University of Washington, has been sort of in the direction of finding and solving convex relaxations of this problem. So it's a non-convex optimization problem. And along the way, sort of uncovering conditions under which the relaxation would correspond to the actual global optimum of this problem. On the other hand, so even with great ways to solve this problem through convex relaxation, for example, again, implicit in its formulation, as in particular in the formulation of this mapping G, this nonlinear power flow mapping, is that we had access to an accurate model of the system. And this model of the system is kept up to date with respect to, again, I keep repeating myself, but with respect to line parameters, switch statuses, and all sorts of other load levels, DER outputs now, DER capabilities, operational limits, etc. So you can well imagine that in reality, it would be very difficult to do this, right? To keep an offline model up to date, especially considering just kind of the complexities and maybe just the sheer volume of the different devices and parameters that may vary over time. So with that in mind, here we show kind of a numerical example that highlights what a model discrepancy can do in terms of this optimal DER dispatch problem. So here we formulate precisely that problem that I described on the previous page with the nonlinear power flow equations. And so here we use a 33 bus system and there are 5 DERs attached to it and it's shown on this diagram on the top right. And what's notable here is that there are these switches and switch 3 and 4 are normally closed as shown in this figure. So we're conducting or performing this optimization with in mind that the switch 3 and switch 4 are normally closed. And but what we don't know is that in fact that model is out of date. And so instead, the system actually has switch 1 and switch 2 closed, whereas switch 3 and switch 4 are open. And loads are actually 25% greater than what we thought they were for the model. So you can see that if you perform this optimization with the accurate model in place, then you get this green circle in terms of a voltage profile for across all the buses or all the nodes in the system. Whereas if you perform the same optimization problem, but you have an out-of-date model, a model that is incorrect, then of course you get some discrepancies in the voltage profile. And more notably, we have at the optimum solution, the minimized cost function with the accurate model is about 10 times smaller than the cost function that we get with the out-of-date model. So in this example, we basically found that the model discrepancy led to this suboptimal operating point. And in fact, this is kind of the best case scenario, right, that we can hope for, a suboptimal operating point. In fact, the outcome may be even more damaging with the voltage constraints or other violations of physical limits. And then this would then cause automatic protection devices to kick in. So circuit breakers that detect higher current, for example, or over voltages, they would, this potentially could then lead to electricity outages for our customers. And this is all kind of could be caused by these discrepancies between the actual system and the model that supposedly represents the physics of the system, right? The physics being nodal, Ohm's laws and Kirchhoff's laws just apply to all the nodes in the system. So the key takeaway message of my talk today is that physics doesn't matter. So now before you kick me out of this virtual room for making such a statement in front of an EE audience, and while I do wish I had come up with it myself, just allow me to evade some responsibility here by confessing, in fact, that I did not. I shamelessly copied it from an anonymous review that we had on a journal paper that we recently published on this topic. And obviously, I've also reproduced it without due permission, given that the source is anonymous. So I've probably committed 2 worst crimes in academia in this one single slide. But I really hope that I can be forgiven because this statement really so very well encapsulates kind of the central tenet of our work and really that of kind of the general direction of data-driven approaches in distribution control. And for those of you with a keen eye, you will have noticed a little asterisk at the end of the statement by now. And this asterisk refers to the fact that the statement only holds if we have reliable feedback. Okay, so what is reliable feedback? And I would say that this comes in two folds, measurements and actuation. And in some sense, we've already talked about the actuation side being, if we have greater integration of DERs, then the controllable outputs of DERs provides us with actuation. And if we can indeed reliably call upon them to, output what this optimization problem gives, then we have the actuation side of this feedback. Okay, so what about the measurements? Traditionally, monitoring in distribution network is very limited. And honestly, I don't think was that much needed given the fact that loads were mostly passive and there was only one-way flow of electricity. So there was very good, predictions for how the voltages would behave across a network. There would be SCADA measurements at the substation or the feeder head where the distribution network connects to the transmission network. There would also be kind of more specialized measurements that are dedicated to a particular measurement at a particular location. So if you knew a load in the system was sensitive to harmonics, for example, you may want to put a measurement to measure harmonics for power quality at that particular location. So things like that, these things we have in the system. And nowadays, lots of North American utilities have installed smart meters. And in British Columbia, in where we are, or where I am, we have 99% of customers who are on smart meters. And these have helped, to detect energy theft, for example. They found a lot of marijuana grow-ops once they introduced or installed these smart meters. And they also provide really good billing for customers so that they can pay the right amount. But really the data themselves are kind of limited in the sense of time resolution and latency. So time resolution being that most of these things collect data only at 15-minute intervals. And a lot of times this is not done in real, like the data is not transmitted then to a central entity in real time. So in general, it could be delayed or it could be actually held and then sent as a batch at the end of the day or something like that. And also it doesn't generally collect voltage information and only sort of power and energy, which is related to billing, right? What we actually pay for the energy. On the other hand, we have these so-called synchrophasors as well. And synchrophasors are collected by these distribution level phasor measurement units, which are called DPMUs for short, or micro-PMUs. And they provide, and this is a really important aspect, which is time synchronized measurements of voltage and current. And the time synchronicity aspect helps a lot because then we know a time-stamped set of measurements indeed reflects a single snapshot of the system. Like they're not collected for different operating points like other types of measurements. Added benefits are that their measurements happen with high frequency, high speed, and high accuracy as well. So these measurements can generally be collected in the sub-second kind of range. Also, DPMUs are not really installed with any particular dedicated application. And in fact, their potential usefulness has been explored in many different settings, like event detection or model validation, topology estimation, just to name a few, right? So these are very good measurements that we can also get in the distribution network. Okay. And so going back to our distribution network then, and suppose now we have some of these DPMUs installed, distribution level phasor measurement units, or micro-PMUs. And the data is the synchronized voltage and current measurements are transmitted to some central entity. And the question now is, can we use this data to help us somehow in the challenges that we outlined earlier in terms of control and monitoring? Okay. And so related work in this area kind of follow a general theme of requiring limited to no offline information about the network or the system, the physical system itself. And on the other hand, the works generally have various requirements on the types of measurements or the availability of measurements or the speed or the various aspects of measurements. And so in terms of the two directions that are relevant to the work from today's talk, in terms of optimal DER dispatch, the data-driven approaches have been proposed for voltage and substation regulation, and as well under this kind of umbrella category of algorithms called feedback optimization. Both of these kind of categories of work requires some knowledge of the network, very little, albeit. It's things like resistance to reactance ratio of lines and some nominal admittance matrix of the network. And these are generally used to compute the gradients of an optimization problem in feedback. Right? On the other hand, there's a so-called area of work called model-free extremum seeking. But in this line of work, the algorithms generally require structured perturbations in the sense of a sinusoid, for example, a perturbation and then as an input and then measured output, and then sort of seeing the correlation between output and input to infer some information about the system. And then in terms of model estimation, on the side of model estimation, PMU measurements have been used to estimate grid topology, the power flow model, and various other system attributes or somehow proxies that represent the model somehow, like linear sensitivities or graph Laplacians. Okay, moving on to the method that we developed then, we take the PMU measurements of net loads. So these are, again, Y. And so I have a hat now on the measurements, Y hat at time step K, as well as the voltages at time step K. And we use these to estimate a linear sensitivity model. And the linear sensitivity model is basically captured by these linear term and constant term coefficients, J and C at time step K. And we do this without any knowledge of the underlying network. And recall that, the challenging part of solving that, non-convex optimal DER dispatch problem was the fact that we had the nonlinear power flow equations in this G. What we're going to do is basically replace that G with this linear sensitivity model. And in a sense, you can kind of think of this linear sensitivity model as sort of a pseudo-power-flow model. And so that the leap of faith that we kind of make is that with this linear sensitivity model in place of the nonlinear power flow equation in this optimal DER dispatch problem, that the output U, this controllable output, indeed can indeed is accurate and can help us control the DERs, serve as the inputs or the set points to the DERs. And in fact, we basically show that with real-time updates of this sensitivity model, that is, it's not just held static, right? Every time step K, it gets updated. With real-time updates, we can sort of buy ourselves or trade off on the lack of accuracy in terms of linearizing a model. Okay, and the key features here are that we made zero use of the network at all, right? And the estimated model actually, so the estimated model here on the left side in this box actually doesn't need to correspond to any physical or working circuit at all. So it's sort of decoupled from circuits altogether. And in fact, so as long as the linear sensitivity model reflects kind of an up-to-date node-to-node sensitivity interaction, then we're golden. And hence this provides us with the measurement side of this reliable feedback that I talked about. And the control U, of course, for the DERs still remains as our the actuation side of the reliable feedback. Okay, so just going into a bit more details on the sensitivity model estimation. So we assume that the measured voltages and net loads are linearly related. And in fact, we also rely on small signal fluctuations in the load that are really inherent to our electricity usage. So if you turn on your oven or turn on and off a light, or your appliances use different amounts of power, then they're inherently, fluctuating. And as sort of hypothesizing that the measured voltages and net loads are linearly related, and then we can collect these linear and constant term coefficients into this bigger matrix H. And what we do is basically stack up past data points to get an overdetermined system of equations where this big Y, capital Y, refers to stacked up measurements of the net loads, and capital X refers to stacked up measurements of voltages, along with this column of ones to accommodate this constant C here. And so we can replace this linear relationship in the box now equivalently with this Y is equal to XH. And an obvious solution to this, or strategy to solve this overdetermined system, is through least squares estimation. So by minimizing the least squares error between the observations and the linear model. But it turns out that because the X here, the big X, the capital X, embeds all the voltage measurements, it turns out that voltages in the system may actually be highly correlated, because given the same operating point change, the voltages kind of behave similarly. They'll go up and down kind of together. And so this would then result in ill conditioning when you're trying to invert this regressor matrix here. So that would render kind of the least squares estimate invalid in terms of its numerical solution. So instead, we use partial least squares method. So this method is basically a twist on the standard least squares estimation, where you project these matrices Y and X onto kind of directions that are pertinent to the estimation. So that it's like a lower dimensional estimation, and then you do the linear square or the least squares estimation on that lower dimensional problem. We also make use of recursive updates, which weighs the more current or more recent measurements more heavily, because presumably the recent measurements are better reflection of the updated operating point, whereas the past ones are obviously out of date. And on the side of the optimal dispatch, or the optimal DER dispatch, remember that we now have, instead of the nonlinear power flow equation in this constraint, in this equality constraint, we replaced it with this linearized version. And the decision variables are still the same as before, X, Y, and U. And So the only thing that we point out here is that we explicitly put a k+1 here as the time step of the decision variable, which is for the next time step. And kind of the assumption that we make here is that this relationship here, this linear relationship that's estimated at time step k, so jk and ck, indeed represents a good approximation to the relationship that would be at time k+1. And given that these measurements are collected in short intervals, then that's a good assumption. That's an okay assumption to make. And finally, the last constraint, this constraint here, just basically couples quantities across time. So we're basically assuming that the non-controllable loads are kind of remaining relatively constant from time k to k+1, and the changes are then just as a result of changing the controllable input u. So what have we accomplished, right? We have zero knowledge of the underlying network. That is, the physics doesn't matter. And it turns out that with good feedback, the linear approximation is sufficient. And we're able to determine the optimal DER dispatch without any knowledge of that physical network model underlying the system. The only caveat here I will mention is that we can only optimize over nodes that we have measurements of. And we just kind of hope for the best in the nodes that are in between measurements. So going back to our example, remember that we had this example where it showed the suboptimal operating point given model discrepancies. So now using the measurement-based method, you can see that now in this voltage plot, these are the x's. They're much closer to the benchmark solution of the model-based optimization with an accurate network. And at the same time, the resulting minimized cost function is also much closer to the accurate version of the model-based optimization. And in this case, we only have measurements at all the DER buses, so the green ones here, as well as the substation, the feeder head here. And so if we had more measurements, actually these results would be much closer than what we're showing here. So these are sort of not as good and will get better if the measurements are more plentiful. So this plot shows basically the final converged solution. And in fact, we had a simulation where we had kind of a time domain, like real time in the sense to try to show the time evolution of the estimation and optimization combination. So here we have time domain plots of the voltage magnitudes at measured buses. So this top plot here, the active power and the reactive power coming from the DERs and the substation. So in this simulation, what we're doing is collecting measurements at 1 second intervals, which is possible with the PMUs. And at 5 seconds, what we've done is activated the DERs. And part of our cost function is that we wanted to track or regulate voltages to 1 per unit. So indeed, after 5 seconds, we can see that the voltage magnitude shoots up to 1 per unit. And then at 10 seconds, what we did was basically change the topology of the system by closing certain switches and opening other switches. And we can see that again, the proposed framework is able to update the estimated model and then further to implement the DER control so that the voltages are again close to 1 per unit. And here we can also regulate the power from the feeder head in this as this line shows here. Yeah, so hopefully, oh, and then this is just sort of a robust version or to show the robustness against delays. Here we introduce an artificial delay between the measurement acquisition and the DER actuation. And so here with 1 second, 2 seconds, and 3 second delays, we can see that the performance is worse, like there is a delay and there's longer time to convergence, but it eventually does converge, right? So hopefully I've convinced you of this kind of framework where physics doesn't matter as long as there is sufficient feedback. And here, so we only had 5 DERs here, and in kind of going back to the distribution network, we addressed this case where there's really relatively low levels of DER integration. And we expect to have much higher integration in the future. And lots of different governmental reports report this internationally even. And so we might have a lot more solar PV, storage, controllable loads, and electric vehicles as well. And why not, right? Why not generate close to where you're using? Because that's, as we know, less losses and, less requirement on expensive asset investments in terms of long distance transmission. So with greater DER integration, of course, comes a growing need for real-time monitoring and control. And so on the side of measurements, then we would likely also see a lot more of these meters come online and be integrated. We'll see greater availability of synchrophasor data, and especially considering the phasor capabilities can in fact be built into inverters that interface DERs, as well as protection devices like relays. So this kind of motivates us to look at scalability of our method. And for a sense of scale, we basically looked at this 874 bus test system, which has DERs and PMUs installed on it that we put in artificially. And we report the execution time required to update the linear sensitivity model and to solve the DER dispatch problem, and using ADMM or alternating direction method of multipliers, which is our implementation. So Severin implemented this. And we solve the, for comparison, we also solve the DER dispatch using this quad prog function in MATLAB, which is an interior point method. And so you can see that as the number of DERs grow, the amount of time it takes obviously also grows. And at some point around 100 DERs, it's sort of breaching the limit of being able to call this real time, because the estimation and the optimization take on the order of a second or more. And the measurements are collected on the interval of 1 second. And so it's really, stretching that statement of real time. So obviously we're motivated to come up with a scalable method, and the idea to do this is very straightforward. We simply, if we can't solve a giant problem on its own, we break it into several smaller problems and solve them in parallel, right? And the idea to do this comes from, in fact, sort of domain knowledge of the power network. So remember that we're estimating this linear sensitivity model, and the bulk of the estimated quantities are in this matrix J. And J is very strongly related to the topology of the system. And if you look at the topology of this network, you can see that most of the nodes are actually connected to very few other nodes, right? 2 or 3 or 4 at most. And so this matrix J turns out to be sparse, block diagonal, because it really only has interactions with neighboring buses. And if we did split up this system into multiple areas, we find that there are very few boundary buses. And so the idea is then we're going to, instead of estimating this giant matrix J, we're going to estimate like little blocks of the matrix J. And here we use our domain knowledge to inform the methodology that we can indeed break it up into separate problems, but at most also to kind of find an intelligent way to break up the system. But to estimate each individual per area sensitivity model, we're still not relying on any sort of knowledge of topology or network parameters. So the per area sensitivity models then kind of naturally leads to a decomposition of the optimization problem that follows. And so here we can see the problem formulation before on the left-hand side and the problem formulation after on the right-hand side. And there's really a very nice one-to-one correspondence between each of the constraints or the objective function, going from a whole system model or whole system system-wide optimization to a optimization problem that's amenable for decomposition into parallel operation amongst the areas. And just the only thing that's really different is this consensus constraint. So if we were to implement ADMM algorithm on this, and distributed ADMM also comes very naturally, consensus-based ADMM, this constraint enforces that the voltages at the boundary buses amongst adjacent areas to be equal. And so this is kind of one thing that we have to exchange information amongst the different areas, the neighboring areas, so that they can make sure that those voltages are indeed equal at the boundary buses. Right, so what have we accomplished? Again, we are still dealing with this problem of determining optimal set points for DERs. And as before, the problem is constrained by these approximate linear sensitivities, which requires zero knowledge of the physical circuit model. And in addition, now we are able to solve per area problems using consensus-based ADMM, and this can be done in parallel. And each subproblem only needs the per area sensitivity model. And again, the sensitivity models are also estimated in parallel. And so the only thing is that now we need communication between the adjacent areas about the boundary buses. Okay, so to illustrate kind of the effectiveness of this, we looked at a 133 bus system. It's a multi-phase system, it's a three-phase system, unbalanced. And we introduced controllable DERs throughout the system. We assume that measurements are available everywhere. This is actually to just stress the computational overhead. We don't need it. And as we showed earlier, with very few measurements in the system, 5 out of 33 buses, we were able to get pretty good results already. So this is definitely not needed, but just to actually kind of show a worst case scenario. And also to stress the algorithm, we introduced uncontrollable solar PV at various buses throughout the system. And this is, we purposefully took a very choppy output. And so plotted here are the normalized outputs from the solar PV that we included in across the system. So here our cost function, so we're doing this using consensus-based ADMM. Our cost function minimizes the active and reactive power deviations from reference values at the substation, as well as the cost of DER outputs. So on the left-hand side, there's no DER control. So it's just letting the system do whatever it does. And you can see that there are some violations of the voltage magnitude if we set the limit to 0.95, which is typical. So there are some voltages that go below that. And on the right-hand side, we see that with our DER, our estimation plus optimization framework, we can see that there is good amount of control, except for the areas where, or the regions where there's lots of fluctuations in the solar PV. And this is because of that assumption that we made that, the model, the sensitivity model estimated at time step K in this case, cannot represent the system at time k+1 because the solar just changes so quickly. So one way to avoid these fluctuations is to reduce the amount of time between measurements and between actuation. Other possibility may be to pair this method with like a local controller that just acts on the DERs themselves. In terms of timing, so this table here shows that the centralized model estimation takes about 4 seconds, whereas the distributed one takes 100 times less than that. And in terms of the optimal dispatch, it's about a 10-fold improvement from centralized to distributed. So in summary, we've developed this data-driven optimal dispatch framework consisting of estimation and optimization steps. And we have a centralized solution for the scenario with few PMU measurements and DERs, and we estimated reduced linear sensitivity model in this case. And we solve a convex optimal DER dispatch problem that doesn't need crazy optimization algorithms or anything, just any sort of off-the-shelf optimization package would be able to solve this sort of thing. The distributed solution then comes almost for free for for the scenario with lots of measurements and DERs. And here we've exploited the structural properties of distribution network and used consensus-based ADMM with inter-area exchange of information. So the key benefits, I stress again that we have accurate DER set points compared to the model-based benchmark with an accurate model completely known. We incur lower computational complexity because we're solving now this quadratic linearly constrained quadratic optimization problem. The method is adaptive to network reconfigurations and operating point changes because it only uses measurements, right, instead of some knowledge of the system. So obviously it does not rely on an offline network model. And all that is to say, again, the take-home message is that physics really doesn't matter as long as we have reliable feedback in the form of measurements and actuation. And I hope I've been able to convince you of that. And in terms of future directions, we're looking forward to developing actual software with Imbala to facilitate field deployment. And Severin has actually done some demonstrations already with the cloud-based software that they have, the DER management system that Imbala has created. We would like to include other data sources that we talked about, like SCADA, smart meters, and other pertinent measurements. And I think also a really kind of compelling area for research is to incorporate our estimated models in sort of any number of more model-based approaches, like feedback optimization, where they require this gradient to be the gradient of the objective function to be updated in the feedback law. And we think that if we incorporated the estimated model, that could help that algorithm be more adaptable as well. So in general, I mean, greater integration of DERs will, in general, require better real-time monitoring. And on the flip side, the greater availability and quality measurements that's coming from distribution networks will kind of present a lot of opportunities to develop data-driven approaches, which then in turn will help us coordinate those DERs that are coming online suitably towards optimizing the system operation from the grid edge. So that's all I have for today. Thank you for your attention.
Great. Thanks, Christine. Let's all give her a virtual round of applause.
I just realized that there are like these
Oh yeah, there's little questions that come trickling in, and that's fine. That we just let them kind of build up, and we can work through some of these. Let me see here. So there was some playful banter.
That's really funny.
Bashing physics. And let me see. All right, I think Amy Heidner had a question about, are there network topologies which will likely break this non-physical model? So have you run into that before?
No, network topologies will likely, I don't think so, because, I guess it depends on what you mean by breaking. Is it that, because, again, we're kind of decoupling the physical network from sort of a cyber network of measurements, right? So we're really just looking at node to node interactions. So it is possible, I guess, that for some topology, the node to node sensitivities that we collect at this higher, at this cyber level or data level doesn't reflect the actual operating point somehow, or doesn't, no, it always reflects the operating point, but maybe it doesn't, it is not sufficient to capture the entire system so that you can actually implement accurate controls, sufficient controls. So
to follow up on that question, I guess maybe the question would be, is the system always controllable, right? Or is it always observable? And, there certainly would be situations where you could cook up networks that weren't controllable, I guess, right?
yeah, and I think the answer to that is that, again, we're not controlling all the nodes in the system. We only control the places that we're measuring, and we're hoping for the best in the other places. So, for the case of the 33 bus, where we only had 5 measurements, I'm sure we didn't have observability actually, or controllability, but it in fact is fine, because we're, again, exercising domain knowledge that if we, are able to hold up the voltage at, a number of places in the network, then the rest hopefully just kind of follow.
Okay, and maybe instead of me just reading these chat things, I'll invite people to just bravely unmute themselves and just ask questions by voice. And if I don't get any takers, I'll read the next one. Okay, there was a question about why do you think the DER goes from 0.37 seconds at 80 DERs to 1.12 seconds for 100 DERs? This seems like a big jump. I guess there's some availability question. Maybe you had one of these tables where you were comparing.
Yeah.
Maybe there was some runtime.
Yeah, this one, right? And the jump from 80 to 100.
Yeah, I guess it's this TIP on the right-hand side. It went up quite a lot for that.
Yeah, I honestly don't have a good answer for this. This is, simply, again, because our optimization problem is quite simple, we're just using, in the case of the right-hand side, just the MATLAB code or MATLAB function to solve it. So it just happened to jump up there, I guess. And then in terms of the ADMM in the middle, that's Severin's implementation. So that, of course, depends on his coding abilities and whatnot that way.
All right, cool. Anyone have any voice questions?
Yeah, so I was actually wondering if you looked beyond linear models at all for this estimation problem. For example, did you look at neural networks or kernel methods or anything like that?
We did not. Early on in the research, we looked at a quadratic model. But we kind of threw that out early on because there wasn't much more improvement that we saw between linear and quadratic. And that's because I think the fact that we have measurements so often that the linear assumption, the error in that is offset by the updates in measurements.
Thanks.
And I guess there was a question about if you could repeat what was the name of the companies you were collaborating with?
It's a company called Enbala, E-N-B-A-L-A. They were recently acquired. I mean, recently as in last October, I think. And it's a startup that started with this man named Malcolm Metcalf, and he actually lives in Kelowna, which is where UBC Okanagan is, and that's how we have that connection, I guess.
Okay, cool. I got one last question here. Should or is the industry headed towards making all of our sensors, communications, and controls around single phase measurements, single phase modeling, single phase optimizing, dispatch, due to the amount of anticipated distributed single phase DERs? So is this moving to the single phase realm, I guess?
The single phase realm or like per phase realm?
Yeah.
Is the question saying, will we still have a 3-phase system, but have measurements from all 3 phases, or that we'll just forget about the 3-phase and go to a single phase?
Hey, this is Patrick Fowler. I'd like to, let me just chime in because I guess I know what Max is asking. Are these applicable, or maybe not, but hopefully I add something. Could these be, or should these be applicable to the numerous single phase DERs that are being implemented or deployed?
Oh yeah, absolutely. And in fact, in this, I didn't have time to go into like super detail about the description of this system that we have. In fact, even in this test system, Severin's implemented, so you can see like these different colored boxes. So the black is for 3-phase DER, orange and whatever cyan, green are single phase DERs in A, B, and C. And so he already has this in place. And so, you know, the model, again, it's just a sensitive, it doesn't really have that much to do with the network, right? It's just a sensitivity model that looks at effects of one node on the other. So it could be a single node or a single phase node or 3-phase node.
So I'll follow up on that. So what if, so is there some threshold for maybe the size of DERs that should get these sensors placed on them at this point, just for cost benefit or computational cost at this point, do you think? Yeah.
Yeah, I guess that would make sense, right? You would want to have perhaps like, you know, especially considering also if you have a larger capacity of these DERs, like in a single device, that presumably you also have better nuanced control in between, different from the lowest capacity to the max. So yeah, I think there would be kind of some selection, you know, an intelligent way to select different DERs based on their characteristics.
Thank you.
But I guess like I also want to emphasize that like sort of this distributed method or the algorithm that we're going for is to try to not discriminate, I guess, between or amongst the different DER technologies. We're trying to come up with a method where you can plug in DERs and then take them out, and just kind of more on the fly type of algorithm, which is why it's nice that it doesn't have much to do with the physical network.
All right, great. Thanks, Christine. I guess that was the last question I had here on the chat. So unless anyone wanted to jump in real quick, I think we'll go ahead and conclude here. And so, yeah, thanks, Christine. Appreciate it.
Thank you. Thanks everyone for the questions.